Right. So, conservation of mass then, remembering again our parcel and the flux of mass in and out. The change in the mass, d dt, is obviously a rho times the volume, density times the volume, equals d rho dt times delta x, delta y, delta z. That's the net mass flux into the volume. What is the mass flux? It's minus d dx of rho u delta x delta y delta z, just the way we did before. We've already done the delta x minus half delta x plus half delta x, Taylor expansion, and the subtraction to get the net fluxes. And these are the three directions. So d rho u dx, d rho v dy, d rho w dz, right? So those are the three fluxes. And you can write that again using our vector notation, minus grad dot rho u delta x delta y delta z. Put the two together, time rate of change of density. We have taken out the volume and writing it per unit volume, so it's still mass conservation but just being written per unit volume, plus divergence of rho u. So this grad dot rho u is essentially divergence of rho u, right? You have an intuitive sense, convergence and divergence. So change in density at a point in a parcel is the time rate of change and the physical convergence or divergence. So when we say divergence, if it has negative sign, obviously it's convergence. If it has positive value, obviously it's divergence. Okay, so deconcentration dt plus divergence of the flux equals 0. Why do we write it this way? Because this is a common form of many of the chemicals that may be in the air, dust or CO2, or in the water it could be salt. Of course you tend to have sources and sinks, but if there are no sources and sinks, then any particular ingredient or material in the air and water can be written as a conservation equation of deconcentration dt plus divergence of flux equals 0. So let's expand out the divergence term. Rho, so you know how to expand that exactly like this: rho divergence u plus u dot grad rho, that's the gradient of density. So what did we do here? We took the u dot grad rho with dr dt. So remember this equation, dr dt plus u dot grad rho is going to give us the substantial derivative or a Lagrangian derivative or the total derivative d rho dt plus rho times divergence of just the fluid. Okay, this was the divergence of the mass flux. This is the divergence of just the fluid. We just rearranged it, right? Why do we do that? Because this allows us to say some pretty amazing things about when the fluid is compressible versus non-compressible. When the fluid is incompressible, we typically make a simplification that d rho dt doesn't change, so divergence of u is equal to 0. So a non-divergent fluid, for example in the ocean, it's easy enough to make the assumption because ocean is incompressible, ocean water is incompressible. So d rho dt plus rho dot divergence u becomes 0, then divergence u can be considered 0. It's not exactly valid all the time because you can still have internal heat sources and buoyancy changes and so on. But even if the fluid parcel moves from one place to another, one density to another, because of internal buoyancy changes, it need not perturb the conservation of mass. So this is about conservation of mass. Can conservation of mass be satisfied by assuming divergence u equals 0? It most certainly can in incompressible fluids. Okay, that doesn't necessarily mean d rho dt is 0. So this is kind of a detail, but we will see. So divergence u then is just du dx plus dv dy plus dw dz. So incompressibility basically means non-divergence. So you cannot entrain bubbles because that makes it compressible, right? If you have air bubbles, cavitation, for example, then it's not incompressible anymore. As I said, this doesn't necessarily mean the rho dt equals 0. There are details you can read up, but if you just remember that incompressible assumes that there is no direct cooling and reducing the temperature and increasing density. For example, in ice formation, when you form sea ice, the salt in the water is rejected as water freezes and the molecules get arranged nicely to make it lighter than water, for example. Brine is rejected. The colder it gets, the more compact the structure gets, the more salt will be rejected, and so on. So increasing salinity there changes density, and the water immediately below is going to receive that salinity and change its density, right? So then it's not incompressible anymore. So incompressible fluids, mass conservation equation can be approximated by non-divergent motion. You have to be careful when you apply it, but in most of the ocean problems we do that. But now when you do full climate, obviously there are other approximations involved in how vertical motion is affected. I won't go into it right now, but we'll come back to it later on.